Okay, so in the last lecture or video, we have seen how to find eigenvalues for X gate. I made a mention that there are Y and Z gates as well. So let's see how to find, because that video has become lengthy. I'm doing it in the next video. Let's see how to find eigenvalues and eigenvectors for Pauli Y gate. First of all, let me give the notation for Pauli Y gate. It is something like 0, I, minus I, and 0. Okay. Those who have seen, those who are aware of basics on quantum computing, all of you would be knowing that ket0 stands for the vector 1, 0, and then ket1. These are the basic single qubits. Okay. Ket1 stands for 0, 1. Ket0 stands for 1, 0, and ket1 stands for 0, 1. Now, usually, I'll make a mention here that usually we call this Pauli Y gate to be state flip, and phase flip. Let me explain this and go to the process of finding eigenvalues and eigenvectors. State flip and phase flip. Okay, so actually state flip. Suppose if I take out I common, it is like 0, 1, minus 1 and 0. Okay, so I can clearly see that this is ket1, and then with a negative sign, this is ket0. Okay, so state flip is 0 and 1 are being flipped. That I can see in the columns of the Pauli Y gates, 0 and 1 are flipped. Coming to phase flip, let me put it in a very easier way. Suppose I have this way of representing theta is equal to 0, theta is equal to polar way of representing, or whatever, theta is equal to pi. Now, if I see here, cos 0 would be 1. Okay, of course, cos pi by 2 would be 0, as all of you know. Cos pi would be minus 1. So, here I can see that there is a state flip. This from the state ket0, the state ket0 and ket1 are flipped. Along with that, there's a phase flip as well, because see, I've started at 0. Okay, there's a flip of phase to pi. Hence, my 1 has become minus pi. Like that, Y gate, usually to remember, because there are too many gates, half a dozen gates, at least in two qubit, half a dozen gates are there. So, important ones. So, to remember them, this is the way we will go. We will interpret to remember. Okay, let's go for finding out the eigenvalues. How do I find eigenvalues? Of course, for time being, I'll call this to be A. The equation to find eigenvalues. To find eigenvalues, what do I need? Okay, det A minus lambda is equal to 0 is the equation that I need. Okay, so how will it be like is minus 0 minus lambda minus I 0 minus lambda, determinant, this is equal to 0. Okay, so if I go with AD minus BC format, lambda square plus I square is what I will have, is equal to 0. As all of us know, I is equal to under root of minus 1. I squared would be minus 1. Okay, hence lambda square minus 1 is equal to 0. If I resolve it into roots, lambda plus 1, a square minus b square format. So a plus b into a minus b. Okay, hence lambda is equal to minus 1 comma 1. Now, let's find the eigenvalues for lambda is equal to 1 for a Pauli Y gate. Eigenvectors. How do I find? Using the eigenvalues. For lambda is equal to 1, lambda is equal to 1, let ket xi be the eigenvector. Of course, what does ket xi stands for? That also I should write. Ket xi is equal to alpha, beta, be the eigenvector. Then what? I have the eigenvalue lambda 1, of course. Okay, then what? A ket xi 1. This is equal to lambda 1 ket xi 1. Okay. Yeah. So I'll proceed. So I'll be having 0 I minus I 0. Ket xi 1 is alpha beta. I have considered lambda 1 to be 1. So RHS also will be alpha and beta. Okay. So what happens in the equation format? First, minus alpha is equal to minus alpha I. This is minus alpha I. Just a second. 0 into alpha. 0 into alpha minus I beta. This is equal to alpha is the first equation. Second equation is I alpha plus 0 into beta is equal to beta. Okay. So what do I get from this? 0 into alpha is 0. So minus I beta is equal to alpha. Okay. From this what I have is minus I alpha is equal to beta. Best thing that I cannot interpret anything from it. So best thing what I will do is I will substitute the value of alpha in the second equation from the first equation. So what happens is I is there in the place of alpha. I am substituting minus I beta. Okay. This is equal to beta is what I have. I into I is I squared and I know I squared is minus 1. Minus of minus 1 would be plus 1. Beta is equal to beta. Okay, this is what I get. Okay, beta is equal to beta. Of course, this is a positive sign. Now, I also have this relation, guys, when I'm talking about the Bloch sphere and all, or when I'm talking about the Ketzai, the superposition form of Ketzai, where Ketzai is alpha ket 0 plus beta ket 1. When I'm talking about this version, I also make a mention that mod alpha square plus mod beta square value is equal to 1. Okay, also this version is same as alpha square plus beta square. Under root of alpha square plus beta squared is equal to 1. Okay, so that version if I consider and rewrite for alpha and beta, then what I will have will be alpha is nothing but I beta squared, right? Minus I beta squared. So minus I anyways gives me minus I beta whole square plus beta squared. This is equal to 1. Okay, so anyways, this gives me what? Under root of beta squared plus beta squared, which is equal to 1. Of course, from this also, I have something like that only. Okay, so what I will have is under root of 2 beta squared is equal to 1. Squaring on both sides. By squaring on both sides, I will have 2 beta squared is equal to 1. I will write here in shortcut, squaring on both sides. S dot b dot s also can be written squaring on both sides. I'll have what? So beta squared is equal to 1 by 2 or beta is equal to plus or minus root 2. Plus or minus 1 by root 2. Okay. Of course, I can take anything. Anyways, I'll be satisfying this relation. So accordingly, I'll be taking. Now, what would be alpha? Okay, alpha is equal to minus I beta. Na? So minus I 1 by root 2. If I am taking beta is equal to 1 by root 2, then alpha would be what? Minus I by root 2. Okay, I can go with the other version as well. It depends on where you are measuring. Of course, as I may mention in the initial introductory videos, where I'm measuring, depending on the state of measurement, the values would be considered. In general, I am taking, anyways, I have considered ket xi 1 to be alpha beta, a vector. Okay, so here I am just considering minus I by root 2 and 1 by root 2, or I can rewrite this as 1 by root 2 minus I and 1. Okay. If I consider 1 by root 2, if I consider minus 1 by root 2, then things would be different. Okay. For the next eigenvalue, for eigenvalue, lambda 2 is equal to minus 1, let get xi2 be the eigenvector. Of course, again, I'm taking it in the form of alpha, beta. Of course, you can go with the suffixes alpha 1 and beta 1 for ket xi1 and alpha 2 and beta 2 for ket xi2. Just to make things look simple, I'm considering this version. Okay, so what I will have in the A would be 0 I minus I 0 alpha beta, and this is equal to it's multiplied by minus 1, so alpha beta. Okay, so I'll be having again minus I beta, this is equal to minus alpha. Okay, of course minus gets cancelled and I'll be having I beta is equal to alpha. Similarly, I alpha is equal to minus beta. Okay, I alpha is equal to minus beta. Again, the same thing. I will substitute from both the equations. I'll be substituting the alpha value in the second equation from the first equation. Okay, so I into I beta, this is equal to minus beta. Okay, so again, it results in beta is equal to beta. I will go with this version where mod alpha square plus mod beta square is equal to 1. Okay, so what I have got is mod alpha square is nothing but mod alpha square. Just see here, I am in complex or imaginary number. So mod alpha square is nothing but my alpha into alpha conjugate plus beta into beta conjugate, guys. This is okay. It is not just, it's not a real number. So it is not just the square, it is the conjugate. Of course, if beta is real, then I will take a conjugate of a real number is itself. So beta would be beta only. Similarly with alpha also. Now, alpha is what? I beta. Its conjugate would be what? Minus I beta. Okay. Plus beta is beta is equal to beta only. Okay. Nothing like I or something like that. So beta is beta only. So it is beta squared and is equal to 1. So what I will have here finally is beta squared plus beta squared is equal to 1, or 2 beta squared is equal to 1, implies beta is equal to 1 by root 2. Of course, again plus or minus 1 by root 2. Okay. Now, if beta is equal to 1 by root 2, what would be alpha from this equation? Alpha is equal to, if beta is equal to 1 by root 2, then alpha would be what? I beta, which is equal to I by root 2. Hence, ket xi2, the second eigenvector for lambda is equal to minus 1 would be alpha is what? I by root 2. Beta is what? Beta is 1 by root 2. Hence, I will have, if I take 1 by root 2 common, I and 1. Okay, I can see the other eigenvector as well. This is how I'll be finding the eigenvalues and eigenvectors for any gate. Okay. Of course, where and how we'll be using them, let us see in the next concepts. Okay. Yeah. Next, we will see how to find the eigenvalues for the Pauli Z gate. For Pauli Z gate. Okay. Again, what's the difference between X, Y, and Z? Z, let me write first. How will my Z gate look like? Let me write that notation first and then go to the different explanation things about it. Okay. Yeah. The Z gate looks like this. It's nothing but my 1 0 0, minus 1. Okay. What it is said here is no flip of state. Why? Because as explained in the beginning of this video, this is ket 0, this is ket 1 only. 1 0 is ket 0, 0 1 is ket 1 only. No flip of state, but flip of phase. Flip of phase, because there is a negative sign. That's how Z is remembered. No flip of state, but flip of phase. X is flip of only state. Okay, Y is flip of state and phase. Z is no flip of state, but flip of phase. How do I find eigenvalues? Again, the same thing. I'll be using det Z minus lambda I is equal to 0 format. So I'll be having 1 minus lambda 0, 0 minus 1 minus lambda is equal to 0. Determinant. So what are the eigenvalues? Just see. 1 minus lambda. Of course, I can take out minus and I'll be having 1 plus lambda. There is a multiplication sign in between. Okay, I hope I'm not confusing. A minus B into A plus B format. 1 square minus lambda square is equal to 0. Lambda is equal to plus or minus 1 are my eigenvalues. Okay. Hence, I will be finding eigenvectors. Immediately without loss of generality, I will be going with eigenvectors. Again, the same notation where Z into ket xi1. This is equal to eigenvectors for which I will be considering lambda 1 is equal to 1 or minus 1. Anything is fine. Ket xi1. Okay. Of course, I know ket xi1 is what? Alpha, beta. Okay. Yes. So, I have 1, 0, 0 minus 1 into alpha, beta. This is equal to alpha, beta. Okay, let me write it in equation format. So what I'll be having, let's see. Yeah, alpha plus 0 beta is equal to alpha. 0 minus beta, this is equal to beta. Okay, so I have alpha is equal to alpha and beta is equal to minus beta. Okay. So anything I can substitute. Alpha is equal to alpha and beta is equal to beta. So eigenvalues are beta is equal to minus beta. So I can say that if I take alpha is equal to 1 and beta is equal to minus 1, I can just say that the eigenvector is 1 comma minus 1, or the eigenvector is 1 and minus 1. Okay. Therefore, because there are no i's and all that, I need not to go checking with this whether it's satisfying or not. So ket xi1 would be what? 1 and minus 1. Okay. Next, let's see. For lambda 2 is equal to minus 1, ket xi2 be the eigenvector. Again, ket xi2 be alpha, beta. Okay. So what I will have is 1, 1, 0, 0, minus 1, alpha, beta. This is equal to minus 1 and 2. So minus alpha, minus beta is what I have. Here I can just write, guys. See here. If I take beta towards right side or add beta on both sides, then it is 2 beta is equal to 0. Okay. So beta is equal to 0. That also alpha is equal to alpha only. So I can put here 0 as well. Alpha is equal to alpha. So let it be some k. So 1, 0, k is what can be my eigenvector. Okay. So here what I'll have, alpha is equal to minus alpha. That's it now. Alpha 0 into beta. Alpha is equal to minus alpha. 0 alpha minus beta is equal to minus beta. Okay. From this, I cannot say anything. Okay. Because it results in 0. From this, I can say alpha plus alpha is equal to 0 implies 2 alpha is equal to 0. or alpha is equal to 0. Okay, so I'll take some non-zero value for beta. Let beta is equal to k2. Hence, the eigenvector becomes, get xi2. What it becomes is 0, k2 or 0, 1 into k2. Okay. Hence, the eigenvectors are 1, 0, comma 0, 1 for Pauli Z gate. Okay. Yeah. Now with this, I will stop here and then come back with the other gates. One or two looks difficult gates, but then once you keep solving, they'll be easy. Thank you.